Imagine, you need to translate a page of text from English to French, but there's a rule. First, read the entire page and write down the meaning in one sentence. Now, try to produce a full translation using only that one sentence. Sounds absurd? That is exactly how neural translation worked before 2014. An intern in his early 20s, a Belarusian named Dzmitry Bahdanau, removed that limitation and accidentally laid the foundation for everything we now call GPT. Of course, from this idea to ChatGPT, there are dozens of breakthroughs, but without it, the path would look completely different. But first, why is machine translation so hard? And why have people been struggling with it for 70 years? January 7th, 1954. Georgetown University and IBM put on a public demonstration. An operator who knew no Russian typed 60 Russian sentences into an IBM 701 computer. The machine translated them to English using just 6 grammar rules and a vocabulary of 250 words. The press went wild. The lead scientist predicted full machine translation within 3 to 5 years. It didn't happen. 12 years later, a government committee called ALPAC declared machine translation useless and killed funding for nearly 20 years. The dream froze. One system made it through, SYSTRAN, built in 1968 for the US Air Force to translate Russian military documents during the Cold War. Hand-coded grammar rules, brittle, unnatural. Every new language pair required years of expert linguists writing rules by hand. But it was good enough to keep going. Then, in 1990, a team at IBM had a radical idea: stop writing rules by hand. Let the machine learn translation from data. The idea behind statistical translation: take millions of sentences that humans have already translated, Canadian parliamentary debates in French and English, United Nations documents in 6 languages, European Parliament proceedings from 1996 onward, and count. How often does the French phrase pomme de terre appear next to the English potato? If it happens 10,000 times, that's probably the right translation. No understanding, no grammar, pure probability. This approach led to Moses, an open-source system released in 2007 that became the gold standard for a decade. Moses was not a neural network. It was a massive engineering pipeline. Split a sentence into short phrases. Look up each phrase in a giant table of translations built from those parallel texts. Score every possible combination using a language model and reassemble the result in the right word order. Tens of thousands of engineering hours, hundreds of hand-tuned components, a separate program called GRUs just to figure out which word in one language corresponds to which word in the other. And it worked, well enough to dominate for 10 years. And then came Google Translate, launched in 2006, powered by the same statistical approach, not Moses itself, but the same idea. Learn translations from massive parallel data. Google built their own version, led by Franz Hoch, who was one of the top experts in statistical machine translation. By 2016, 500 million users, 100 billion words translated every day. Incredible scale, but the quality? Let's just say fall protection sometimes became autumn protection. And the Norwegian Olympic team once ordered 1,500 eggs through Google Translate and received 15,000. Statistical translation, whether Moses or Google's version, had hit its ceiling. It could look up phrases and rearrange them, but it couldn't understand meaning. And that's when neural networks entered the picture. What's different about neural networks? Instead of looking up translations in a table, a neural network learns its own internal representation. Every word gets converted into a vector, a list of numbers that captures meaning. King and queen end up as similar lists of numbers because they appear in similar contexts. The network doesn't follow handwritten rules. It discovers patterns from millions of examples. In June 2014, a team in Montreal led by Bengio, one of the three godfathers of deep learning, who would later receive the Turing Award, the highest honor in computer science, for his foundational contributions to the field. That team published a beautifully simple idea. One neural network, the encoder, reads the input sentence word by word and compresses it into a single vector. A second neural network, the decoder, takes that vector and generates the translation one word at a time. But here's the tricky part. How does the network read a sentence? It can't see all the words at once. It reads them one at a time, and it needs to remember what it's already read. That's the job of a building block called GRU, Gated Recurrent Unit, which Cho proposed in this very same paper. Think of it like reading a long document and taking notes on a single notepad. You can't write everything down, there's not enough room. So you have two filters. The first filter, the reset gate, decides, should I start fresh for this new word or keep my old notes? The second filter, the update gate, decides, how much of the new information do I blend in with what I already have? These two filters are all the GRU has. They let it decide what to remember and what to forget as it reads each word. An older design called LSTM used 3 filters and a separate memory cell, more complex, more powerful for very long sequences, but slower to train. Cho's GRU was simpler, about 20 to 30% faster, and on most tasks, just as good. Elegant, simple, and broken on long sentences. Here's the problem. The encoder reads the entire sentence and compresses it into one vector of fixed length, one set of numbers, whether the sentence is 5 words or 50. Everything gets squeezed into the same container. It's like being given a suitcase and told, pack 1 paragraph. Fine. Now pack an entire chapter. Same suitcase. The information simply doesn't fit. Translation quality is measured by a metric called BLEU, proposed by IBM researchers in 2002 and used as a standard ever since. It's a score from 0 to 100 that tells you how close a machine's translation is to what a professional human translator would write. 30 to 40 means understandable and decent. 60 to 70 is the level of a living translator. Why not 100? Because even 2 professionals will translate the same sentence differently. Different words, different order, both correct. Perfect agreement doesn't exist even between humans. The encoder-decoder without attention scored around 18. That's the level of you can maybe get the gist, but the grammar is a disaster. And on sentences longer than 20 words, quality dropped even lower. So what did Bahdanau come up with? 3 people were working on this problem at the University of Montreal. Dzmitry Bahdanau, an intern after his first year of master's studies, in his early 20s. Before this, a gold medalist at the International Olympiad in informatics, 13th out of 300 from around the world. The idea is surprisingly simple. Instead of compressing the entire sentence into one vector, give the decoder the ability to look back at the original text at every step. Not at the compressed summary, at the sentence itself, word by word. Like a human translator who moves their eyes across the original while writing the translation. 4 steps. Let's walk through an example. Say we're translating, the cat sat on the mat into French. The full French translation is "Le chat était assis sur le tapis." Now imagine the model has already generated "Le chat était assis sur le." Everything except the last word. It needs to produce tapis, the French word for mat. How does it decide what to focus on? First, the encoder reads the source sentence both forwards and backwards. Why backwards too? Because sometimes you need future context to understand the word. The word bank could mean a river bank or a financial bank, and the words after it help you decide. By reading in both directions, each word gets context from the entire sentence. This is called a bidirectional neural network, or BiRNN. Second, the decoder is about to write tapis. For this, it asks, how relevant is each source word right now? It computes a score for everyone. The low, cat, low, sat, low, on, medium, mat, very high. These scores are raw numbers. They tell you relative importance, but they're not yet normalized. Third, those raw scores pass through a function called Softmax. What Softmax does is simple. It turns any set of numbers into percentages that add up to 100. So now we know 83% of the model's attention is on mat, 9% on, the rest, almost nothing. This is the attention map. The model has decided to write the word tapis. I need to focus almost entirely on mat. Fourth, the model takes each source word's representation, multiplies it by its attention weight, and adds them all up into one context vector. Think of it as a cocktail mixed, specifically for this word of the translation. 83% mat, essence, a dash of on, a hint of everything else, a completely different cocktail for each word the decoder generates. And this is what the decoder uses to decide what word to write next. Not a single compressed summary of the whole sentence, but a custom-made blend, different every time. And that's it. No hand-coded rules. Unlike SYSTRAN, where linguists wrote every grammar rule by hand, no separate alignment program. Unlike Moses, which needed GIZA ++ just to match words between languages. The entire system learns end-to-end. You feed it translated sentences, and it figures out everything on its own. And, in Bahdanau's own words, it worked from the very first try. Now let's look at the results, honestly. BLEU scores. Remember, 0 to 100. Encoder-decoder without attention, around 18. With attention, 27. Plus 9 points from one idea. For context, the entire field spent 10 years going from 20 to 30. And on sentences without rare words, Bahdanau's model scored 36.15. And for the first time in history, beat Moses. 36.15 versus 35.63. But, an important caveat. When the text contained rare words outside the 30,000 word vocabulary, Moses still won. 33.30 versus 28.45. The neural network didn't crush statistical translation. It matched it for the first time on clean sentences. But that was enough to prove neural translation works. Now, here's where the story gets interesting. What happened in the 9 days, 1 year, and 2 years after Bahdanau posted his paper? 9 days later, on September 10th, 2014, a team at Google Brain, led by Ilya Sutskever, who had just gotten his PhD under Geoffrey Hinton and co-invented AlexNet, published their own neural translation system. They used LSTM, that older 3-filter design with a separate memory cell. Where chose GRU was lean, Sutskever stacked 4 layers of LSTM on top of each other, brute force instead of elegance, no attention. The same fixed vector bottleneck that Bahdanau had just solved. Their trick? reverse the order of words in the input sentence, so the first words of the source end up closest to the first words of the output. A clever workaround. BLEU score 34.8. Good, but below Bahdanau's 36.15. Here's the thing. By the time they submitted, they already knew about Bahdanau's work. It's cited in their paper. They were aware of the attention approach and still chose a different path. Bahdanau solved the bottleneck. Sutskever worked around it. Historically, Bahdanau's mechanism became the more durable line of development for neural translation and everything that followed. 1 year later, August 2015, a PhD student from Vietnam named Sang Luong, working at Stanford under Christopher Manning, arguably the most cited person in all of natural language processing, published an extension of Bahdanau's idea. 2 key changes. First, instead of Bahdanau's neural network scoring, which used a small network to compute each score, Luong used simple matrix multiplication. Dot product. Faster, fewer parameters. Second, he introduced local attention, attending to just a window of words instead of all of them. And here's the twist that matters most. When the team behind the transformer built their architecture in 2017, the architecture that powers GPT, BERT, and ChatGPT, they didn't use Bahdanau's scoring. They used Luong's scaled dot product attention. They say so explicitly in the paper. And after that, everything moved fast. November 2016, Google switches. Google Translate to neural networks using Bahdanau-style attention. Errors drop by 60%. Google's own words, improving more in a single leap than we've seen in the last 10 years combined. June 2017, the transformer. An architecture built, quote, entirely on attention mechanisms, without recurrence or convolutions. 2018, BERT and GPT, both built on the transformer. 2022, ChatGPT, a direct line from a summer internship to the AI revolution. And the most ironic part, the name attention wasn't Bahdanau's. He called his architecture RNN search. In Bahdanau's own words, the better name, attention, was only added by Joshua Bengio in one of the final passes. The most influential term in modern AI appeared almost by accident.